Damos por finalizada la ceremonia de inauguración del 8º Congreso de la Asociación Mesoamericana de Ecotoxicología y Química Ambiental. Invitamos a nuestro honorable Presidium a ocupar la primera fila de invitados especiales. Gracias. Les invitamos a permanecer en este recinto para presenciar la conferencia magistral Impacto de la química analítica en las prácticas industriales, impartida por el Dr. Kingsley Dontor. A continuación, recibamos al quinteto de clarinetes ébano, quienes interpretan para nosotros La Viquina de Rubén Fuentes y Corazón de José Alfredo Jiménez. Queda con ustedes el quinteto de clarinetes ébano. Queda con ustedes el Dr. Kingsley Dontor, quien imparte la conferencia magistral Impacto de la química analítica en las prácticas industriales.
Can you hear me? Good. Okay. I've learned a little Spanish, so buenos dias. Good morning, and thank you all for coming for this presentation. First conference, or Congress, as you guys call it, and I'm really excited to be here. This is my first time in Mexico. Yeah, so it's very exciting for me. And so far, I've really loved Toluca. It's a beautiful city. I think I'm going to come here again and visit. Not to give a presentation, but to tour around. Yeah, so thank you so much for coming, and I'm really, really pleased to share my research with you, which I've done at Thompson Rivers University. Before I start the presentation, I'm going to tell you a little bit about my university, okay, so that you have an idea where I'm coming from. So my university is Thompson Rivers University. The abbreviation is simply TRU, and that stands for Thompson Rivers University. And we are located in Western Canada. And so we have two campuses. There's one campus in Williams Lake, which is over here. The student population in Williams Lake is about 2,000 students. That's a satellite campus. And we have a main campus. The main campus is the Kamloops campus, and that is here. And in Kamloops, we have over 13,000 students. Kamloops is actually about 4 hours drive from Vancouver. Some of you may know Vancouver. And we are about 6 hours drive from Seattle in the US. We also have an open learning branch which delivers online and distance courses to about 15,000 students every year. So in total, our student population is about 25 to 30,000. Just to continue and show you a few pictures of how the university looks like. This is the science building. This is where I'm located. This is where I do all my teaching and my research. We also have a law faculty, and they are located in this building. We have a very large group of international students at Thompson Rivers University. Students from all over the world, students from Mexico and so many other countries. And that is their building there. That is the building which caters to their activities and services them and so on. Then this is called the old main building. We have classrooms here and staff offices in this building. This is activity center, so this is more like a place where the students have cafeteria, the bookstore, the university bookstore, and a whole bunch of offices and space for students to sit down and relax and when they are not in classes. And then this is arts building. So this is the arts and education building. And then this is our library. This library is our new library, which was built about 3 years ago. So it's about it's 4 floors, very nice. And you can see there is a statue of a cougar, right? Because cougars are normally found in our location there in Canada. And then we also have a trades and technology. So students can take courses or programs like carpentry, welding, electrician, and a whole lot of other trades and technology programs. And then, just to show you how, if you're a student and you were to come to our university, where you can stay. So this is one of our halls of residence. We have about 5 halls of residences. So this is one of them. So this is the university. So now, now that I've shown you a little bit of my university, I'm now going to start actual presentation. So on this slide, for this presentation, I'm going to start with an introduction about how analytical chemistry impacts the industry. And I'm going to actually, all of these projects were to improve the processes, the analytical processes in 4 industries listed here. So the first industry is oil and gas industry, and here the target is choline chloride. So that is the compound or the substance that we're looking at. The second industry is mining. So for this project, the target is xanthates. Then the third is fisheries. So for the fisheries project, the target is rotenone. And is agriculture, particularly cattle. And here, the goal is to study fatty acids in cattle. So and then finally, I'm going to end with some acknowledgements. So thank a few people who have made my research successful at the university. So let's start with the introduction. So analytical chemistry actually plays a big role in the industry. It actually provides assurance of the quality and safety and efficiency of the products that are normally obtained in the industry. It actually has a huge impact on the industry, and I'm just going to go through a few of these with you. Analytical chemistry helps us to be able to improve the product quality. It also helps us to be able to improve the process efficiency, and it also ensures process safety, as you can see. And it improves, for some industries, it helps us to improve the design of the plants. Also importantly, analytical chemistry provides scientific information for risk assessment, and that actually is very important for this Congress, right? And it also helps to establish environment to absorb water as well. And that is not a good thing, because it presents a lot of problems. One of the problems is bit balling. We call it bit balling, and that is shown here. So what happens is the clays, which have swollen, tend to actually become soft and sticky, and then they tend to stick to the drilling bits. So as you can see, this is some of the clay particles or swollen clays sticking on the bits. These are the bits they use to drill for the oil and gas. And so it causes a lot of problems in the oil and gas industry. And then the second problem is when the clays do swell, they tend to make the walls of the wells very unstable, to the extent that sometimes the wells can collapse, and that is not very good. Also cost a lot of money in the oil and gas industry, particularly in Canada. Lastly, these bits, or the swelling of the clays, can also cause damage to the drilling accessories, which they use to do the drilling. So in all, in the oil and gas industry, particularly in Canada, this results in a high drilling cost. We're talking about millions and millions of dollars. And also, the production rates are very, very, very slow. So what do they do in the oil and gas industry? Traditionally, in the past, they've always used clay stabilizers, which means they use potassium chloride, and they ingest the potassium chloride into the well, in the water. And the potassium chloride is supposed to prevent the swelling. However, there are some concerns with potassium chloride now, because large amounts of the chloride, which are released from potassium, most of the drilling accessories that are used. And then lastly, the amount of chloride which is released from choline chloride is way, way less. 70 to 75% less than the amount released by potassium chloride. That is why the oil and gas industries are moving and starting to use choline chloride. So, why do I have to worry about this choline chloride? Well, there are three groups which actually impact on this research. The first group are the suppliers of choline chloride, the companies which supply the choline chloride. The second group is the oil and gas companies themselves. And then the third group, ecologists and environmental specialists. So let's go through one by one and see why these three groups actually are very concerned with choline chloride. One, the suppliers. The purity of choline chloride is supposed to be 60% to 100% choline chloride. However, it has been noticed that in the industry, some suppliers actually add salts like sodium chloride, potassium chloride, ammonium chloride to simulate choline chloride. And so basically, these are adulterants, right? So there is adulteration. So you buy a choline chloride from the company, and they might say that the purity is maybe 90%, but truly it's not 90%. It's probably maybe 50%. Okay? The other percentage is coming from these. And so that is the reason why we decided to try and establish an analytical method as a quality control to determine the true amount of choline chloride that we get from the suppliers. The second group is the oil and gas. And the oil and gas companies, as you know, they spend a lot of money on choline chloride for their processes, and they are paying too much for a low quality product. And also, there is a risk in production, right? Because remember I said the walls of the wells can collapse, and that can cause injuries, and it's also cost them a lot of money. So they are always concerned. So they would like to get the true or the true accurate purity of the choline chloride that they use in the industry. Environmental specialists. In fact, there is hardly any ecotoxicity data out there. So there is a need to do a little bit of research. And in the literature of choline chloride on marine life. And so that is why I decided to get into this project. So you might be wondering, are there any methods that the oil and gas companies can use? There are. These are the methods which are currently being used. Titration, ion chromatography, and a gravimetric method called the Renike salt gravimetric method. But these are not very good. I'm going to just discuss the disadvantages pretty soon. But let me take a moment to explain what this method is. This is more like the classical, traditional method used in the oil and gas industry right now, the Renike gravimetric method. Very simple procedure. What they do is they get an ammonium Renike salt, and they get a saturated ammonium salt. Add the Renike ammonium salt with choline chloride, and that gives you a precipitate. So you get a red precipitate, and then you can filter and weigh. So it's a very simple gravimetric method that they use. And then sometimes they can use titration. You guys, I'm sure, are aware of titration. Everybody has done titration in first year chemistry and so on, right? Yeah, so that is the gravimetric method. Why are these methods not that good? The drawbacks, the limitations of these methods. So the limitations are shown on this slide. And you can see they are not very sensitive, like titrations. You are aware how titrations are not sensitive. They are not selective. And determine choline chloride. So in the next few slides, I'm going to describe how these two methods work, but particularly this method, just in case somebody is here who is not very familiar with this method. So Objectives. Our goal here is to develop a reliable analytical method to monitor the choline chloride concentrations in oil processed waters by capillary electrophoresis and LCMS. That's the first objective. The second objective is to establish the accurate purity, right? Establish the purity of the choline chloride in commercial products. This picture here shows you some of the processes which go on in the oil and gas industry. And so you can see here the water, the chemical mixing, the well, and they inject, and then they sometimes get the water out, the produced water, and then they can actually dispose of them. So now I'm going to describe how the method that we developed, how it works briefly. So the first method is capillary electrophoresis. So let's see how this method works. So just as the title says, it's a capillary. So you use a capillary, and the capillary is very, very thin. And the sizes are usually like 50 microns. So think about it like a single strand of hair, right? One single strand of hair, and you are using it for analysis. That is how big it is. And so here you have a schematic of the method. And you have, normally you need an inlet valve to hold the buffer. You need an outlet valve to hold the buffer. And then you also need a high voltage power source, because in capillary electrophoresis, you need to provide a voltage. So, and then this is more like you need your detector, right, to be able to detect your analytes. So the way it works is the capillary, in this case, this is the capillary, is filled with a buffer solution, and the buffer solution has to have a fixed pH. So it can be pH 6, pH 7, pH 8, or 9, depending on what analysis you are doing. And then you apply the voltage. So you apply a voltage, and that generates an electrical field, which generates a current, the buffer solution, to move through the capillary, and that flow is called the electroosmotic flow, which is simply the flow which goes on through the capillary by application of the voltage. And then we inject our sample. So we have a sample vial. So whatever your sample is, water, whatever, you have it here. You inject it, and that goes into the capillary. And then the sample components, or the analytes, are going to be separated based on charge and size. Okay? So the greater the charge, the faster the analyte. The smaller the size of the analyte, the faster the analyte. Okay, so if you have two analytes, the one which is heavier is going to be slower, the one which is lighter is going to move faster and will get detected. So that is how you separate analytes. And then they're going to be detected with a detector. And we get peaks, as is shown here. So think about it as if I had a day. The analysis should look like this. So 3 peaks, each peak for each vitamin. And then the location of the peak will tell you which of the vitamins it is, and the peak area, the area under the peak, the shape, that tells you how much of the vitamin I have. Okay, so that is how this method works. Here shows the picture of the equipment itself, the instrument itself. So here you have the capillary electrophoresis, and it's from Beckman, and then it's computer control. So it's software which controls the instrument. This shows a capillary. So you see how thin the capillary is? So this shows a capillary which is shoved inside a cartridge. And there is a hole here. This is where the detector will sense the samples. And so the sample is going to go through the capillary here, all through here. The sample will travel, and as it travels, they separate, right, based on the size and charge. And then they come here, and then when they get here, there's a detector. And the detector is going to detect the sample, the analytes, and then they come out into the outlet. So that is how it looks like. So this goes into the instrument. And here you can see this placed into the instrument. So you open the lid and you put this cartridge inside the instrument this way. This wire is a fiber optic probe. So this fiber optic probe goes to the detector. This is the detector here. And that detector is a UV detector. So then your analyte has to be UV sensitive for you to be able to detect it. Here shows also the inside of the instrument again. So this is where we put our vials, right? So you have a tray here which has holes. So you make your samples in a vial, put your sample here like you see here, inside the tray, and then your buffer solutions, you put buffer solutions here, and you put your waste vials here. And then you can close the lid and start the analysis. So that's how the instrument looks like. Now let's talk briefly about LCMS. I'm sure most of you have used HPLC in your work. So here what we have is we have LC, liquid chromatography, coupled to a mass spectrometer. So the instrument that I've been using for my research is shown here. So it's an Agilent HPLC, which you can see here, coupled to a mass spectrometer. It's a QTOF mass spectrometer. Here what I'm trying to show is I'm trying to show a column which is in place in the instrument, and there is a Tygon tube which goes from the instrument into the entrance of the mass spectrometer. Okay, so that's the instrument that I've been using. And as you know from theory, in liquid chromatography, the compounds are separated based on their polarity and their interactions with the stationary phase. And in mass spectrometry, the compounds will be ionized. Then we get ions through electrospray ionizations, and they get detected by the quadruple time of flight mass spectrometer. So this gives you an idea how the equipments that I'm using in my research, how they work. If after the talk you want to learn more about the details of the equipment, I'll be pleased to go into details with you. So results. So this slide shows electrophoreograms. Another comment that I should make. In capillary electrophoresis language, we call the peaks electrophoreograms. In HPLC, we call it chromatograms, right? So we use different language in capillary electrophoresis. So this shows electrophoreograms of standard choline chloride concentrations all the way to 2000 ppm. And as you can see, when the concentrations ink bigger and bigger, right, which makes sense analytically. So on this slide are the results. In the interest of time, I didn't put in slides about exactly how the sample is prepared and so on, because I don't have my time. The sample preparation with you after the talk, if anybody is interested. So here are the results. This slide is a busy slide, but there are some points here that we need to take away. In this column, these are the samples, the oil field samples that were analyzed by V, my master's student. This column is the CE results. So you have the percent choline chloride and the percent relative standard deviation. And then here we also have CE results. CE is the capillary electrophoresis. So when you hear me say CE, I'm referring to capillary electrophoresis. So we have that the difference between these two columns is this column was done with external calibration, and this column was done with standard addition. Okay, so these are approaches in analytical chemistry that we use. This column is the results for the, I told you that you form a red precipitate, which is the classical method. That is the results that we obtain. So here we have the percent choline chloride and the percent RSD. So looking at the percent RSDs, you can see that for all of these methods that we developed, percent RSDs are quite low. Look at the C. The highest was 12.8. So the percent RSD is less than 15% with the external calibration. For the standard addition, it's actually the highest is about 978, less than 10%. For the LCMS, it's even lower. The highest is 5%, I believe. For the gravimetric method, so we also use the gravimetric method as a comparison. And here too, we got very decent percent RSDs. So basically what I'm trying to say is the methods that we've developed in our lab are reasonably precise, okay, for the oil industry to use, and better than what they are using right now. which are the titrations, the ion chromatography, and so on. These results are presented even better on the next slide. So here you can see all the 4 methods or 4 approaches, and you can see that majority of them, in most cases, all the 4 approaches, all the 4 analytical techniques compare very, very well. Then recall, at the start I said in the industry, the suppliers sometimes add another chloride like a simulate, right? So it's a little bit of a cheating here to simulate the choline chloride. So we wanted to see if the method that we've developed, the oil and gas company, can use it to actually detect the adulterants, right? The sodium, the potassium, and the ammonium that are added to make it look like the percentage is high for the choline chloride. So here you can see the potassium peak by itself. You can see the ammonium peak by itself. So this is ammonium plus potassium together. And then we bring in sodium. You can see sodium is separated from these two. And then when you bring in the choline, you see that the choline is separated from these adulterants. So the method that we've created or developed in our lab, we can actually use it to detect if the company, that is a very big deal. The oil and gas industry needs to know how much truly the choline chloride is present. So that is the key here. So this is the highlight of the project as well. And in fact, I remember when my student V got these results, the oil and gas companies that I'm working with were really excited, because now they'll be able to tell if they buy the product and they tell them that it's 90%, they can actually determine it and actually find that maybe it's not 90, it's maybe 70%. So the impact on the oil and gas industry is we've been able to develop a method for the oil and gas industry to be able to quantify choline chloride product. So it's a very highly sensitive method. Second industry. Let's see how this project impacts the mining industry. So this is my student Tyson Bodor, undergraduate student. Interestingly, not a PhD, not a master's, undergraduate student, did an excellent work. So here, what are we trying to do? We are trying to determine xanthate compounds in mining. What is the importance of this project as well in the industry? Xanthates. What are xanthates? Xanthates are organosulfur salts, and what they do is in the mining is to extract the mineral, like say gold, copper, or whatever mineral they are looking for. And the way they do that is they throw in the xanthate into the tank, shake the tank, and the xanthates are going to bind. In fact, I have a picture here which shows that. So that's how they do the flotation. And then the xanthates will bind to the gold, for example, right? And then they rise to the surface as a froth. And then they can siphon. This project too is very important because, once again, the mining companies buy the xanthates from some companies, mostly from Asia and a whole lot of other countries. And the companies supplying the xanthates always, and the mining industry, let's say they buy the xanthates from a company, and the company says that the purity is 80%. So the mining industry will start using 80% in all the calculations in their processes. Purity is not correct. So this is where the project comes in. There are 8 xanthates used in the mining industry, and they vary. What happens is the metals, the copper and gold, will bind to the hydrophilic head of the xanthate. This is the structure of xanthates, general structure. And then the hydrophobic tail will form a bubble, and that will carry the gold to the surface of the tank, and when they come to the surface, we call it froth. And then they can then remove the froth and then take it through the processes and actually obtain their gold or copper. So that's how the process works. But like I said, they need to know how much xanthate they have to put in the tank. So if the supplier says it's 80%, and truly the Xanthes is 60%, they are off, right? They don't know the accuracy of their method. So current issues with accuracy, and they suspected that the orders that they are coming from distributors are not properly characterized. The accuracy is not good. And also, remember I said that the common one, the most important one, but sometimes it turns out that there will be other Xanthes present. And so that will skew the accuracy or the purity of the Xanthes. So the objective here is to try and once again characterize the Xanthes I explained to you earlier on that protocol. And here you can see some results. So this is the results my student Tyson got. Excellent results. Look at that. Very separate the Xanthes. So these are 4 Xanthes, nicely separated. So this is the one that they normally need. So even though they will sell it to you as PAX only, there could be other Xanthes present as well as contaminants. Manufacturer's purity claim, they claim that we're totally off from what we determined. And there were large variations between what they claim and what we actually determined. And we actually did this work very carefully. So we think that the results that we obtained are correct. And we also use a second method to verify our values. So the values that we got, we think are actually accurate. And the values on the bags from the suppliers are actually off. So let's go to the third project. And I'm really excited with this third project because this is a project being done by a Mexican student, okay? Iran Ocana. Iran Ocana is from Professor Aberes is in the audience here. And Iran came to my lab this summer to do a summer internship research. And so I decided to give her this project. Very difficult project. And she said, I'll do it. You know, she was up to the task, up to the challenge. And so what Iran was doing was we're trying to determine rotenone in lake waters by using capillary electrophoresis and LCMS. So you're going to see the significance of this project as well to the fishing industry. So what is rotenone? This is the structure of rotenone, very nonpolar. It's a naturally occurring compound derived from plants. Rotenone compounds have been used by people all over the world for centuries to kill fish. Okay, it easily kills fish. And the reason why rotenone kills fish is rotenone gets absorbed through the gills of the fish and then suffocates the fish, and then the fish will die. Okay. However, interestingly, it is not toxic to humans. Okay, because we don't have gills. Okay, look at on this slide. There's some background. There are these fish. Now, this is peculiar to Canada, Western Canada. These are 5 types of fish here: smallmouth bass, pumpkin seed sunfish, yellow bass, and goldfish. These fishes, we call them spiny rays, and they are highly invasive, especially when they are in the lake with salmon and rainbow trout. When any of this, if you ever find any of these fishes in any lake with salmon, they eat the salmon. And they also eat the rainbow trout. So they actually prey on this salmon and trout. These fishes are effective feeders. They simply, and in fact, not only salmon and trout, they eat almost all the aquatic invertebrates in a lake. They just go for them. They are very, and to prove that point, I have pictures here to show that. You see this, I got this picture from the Ministry of Fisheries in Canada. And this was my colleague, my collaborator, Andrew Classen. These are pictures that Andrew took from a dead fish. He opened it up, And this is largemouth. So let's go back a minute. So it's from this guy here, the inside of this guy. You see what he eats? They eat frog. Even the frog in the lake, they just devour the frog. Salamander, shrew, dragonflies, all these were found in the stomach of that fish. So they actually a serious threat to the ecological integrity of the aquatic ecosystems. Okay, so you can imagine how they can devour salmon and rainbow trout. So in Canada, when they realize that the lakes have some of these, they actually treat the lake with rotenone to kill them. All right. So here, solution, and right to kill the spiny ray fish. And what happens is when they kill the fish in the lake, they can then sometimes decide to repopulate the lake with salmon and rainbow trout. So the ministry in Canada always wants monitoring of rotenone in the lakes. So after they've treated the lakes with rotenone, the ministry requires. So this shows a bounty, a harvest of salmon and fish, right? And rainbow trout and a whole lot of other fish. So our hope is to get a method that we can use to monitor rotenone concentrations in lake, that was the project Iran Okana from Professor Averes's lab from UNAM was doing. Hopefully next year I'll get somebody from UAEM, right? Join my lab. Okay, good. So results. Iran, I must say Iran has done a beautiful job, a great job. Remember I said the project was challenging, and I will actually say that I had given this project to 2 students before, and they weren't successful. Iran was successful. So, good job, Mexico. So you can see God, right? Now, in capillary electrophoresis, you have to optimize your experimental conditions. So you have to optimize the pH of the buffer, right? You have to find which pH is suitable for the analysis. So Iran went through a pH of 9.1 to 11. And you can see that at each pH, the results are different. So you can see here there's a shoulder, here there's a shoulder, and there's a shoulder. And Iran decided that this is the best, which I agree, right? So she used 9.5 for her work. And then want to use. So she went through 20 millimolar to 100 millimolar. And you can see here again, the peaks are not the same, right? There's some tailing. You can see here there's a shoulder, and then now it gets better when it comes to lower concentrations. And Iran says this is her best. She likes that one because that is more symmetrical. It gets better when it comes to lower concentrations. And Iran says this is her best. She likes that one because that is more symmetrical. So she used 20 millimolar. And then this is sodium concentration she's using is SDS. Replicates at each concentration level. And you can see the R square very good. And then she did percent recovery. So we had 3 lake samples. So this is large lake. We took the water from the lake from 1 meter down. And then we have the same lake. We took the water sample from 13 meters down the lake. And then beside the lake, there's a pond. And then we took a water sample from 1 meter from the surface. And Iran did her analysis for percent recovery and got excellent percent recovery results. You can see down here her percent recoveries are around close to 100%. And look at the percent RSDs, 4%, 4.8%, and 3.1%, all less than 5%. Very precise work. Okay, very reproducible and very precise work. She also did LOD, which means the limit of detection, the smallest concentration that can be determined with her work, and that was 2.7 ppm, and the LOQ is the reasonable amount that can be determined in the lab, and that was 9 ppm. So the impact here on the fisheries industry, we've now been able to develop a method where the fisheries industry in Canada can actually use to go and determine or monitor the rotenone in the lake with time. okay, just to make sure that they are actually conforming to law. And he is the research chair in Canada for cattle 2016. So what we're trying to do is we're trying to use LCMS. Fatty acids is what we are looking for. So what are fatty acids? The fatty acids that we work on are omega-3 fatty acid and omega-6 fatty acids. This is the difference between the two. Omega-3 fatty acid, the first double bond is attached to carbon 3. Okay, when it's 3. And when it's attached to carbon 6, we call it omega-6. And this end is what we call the omega end. So what we were trying to do is we're trying to develop a method for these two fatty acids. Our diets in the Western world, the omega-6, omega-3 fatty acid ratio is greater than 15. And because most of our diet is rich in saturated fat, when we go to the grocery, in the grocery store or supermarket, put into foods, tablets, cereal. So most of the food products that we have, meat, pasta, sauces, juices, have omega-3 added. And the idea is they want to reduce the omega-6, omega-3 ratio. The lower the omega-6, omega-3 ratio, the better for our health. So why? This is the ratio that is very good for our health. The ratio should be 1 to 4. So why is this ratio very important to our health? Let's go through here and see. Hypertension. When the omega-6, omega-3 ratio is low, less than 4, it lowers hypertension, diabetes. Sclerosis, atherosclerosis is the narrowing of the arteries due to industry to be able to determine omega-3 fatty acids and omega-6 fatty acids, or to be able to determine the ratio omega-6 to omega-3. In the cattle industry, they use GC. However, GC has some limitations. The samples, you need to derivatize, you need to methylate. And GC, we use high temperatures. So the high temperatures may increase the degradation of the polysaturated PUFAs. Liquid-based method, which is LC. So our objective was to develop an LC-MS method as a method to demonstrate or to profile fatty acids in the cattle industry, and to investigate the feeding regimes used in the cattle industry. In the cattle industry, they can feed the cow with grass, or they can feed the cow with grains, right? So we wanted to see, okay, feeding a cow or getting beef from grass-fed, beef from grain-fed cow, which one is better? That's what we're trying to establish here. So we analyzed all these fatty acids with our method, and look at that. We're very successful. We're very happy to do this separation. All the fatty acids were separated. And now on this slide shows the results for grain-fed. So this is the grain-fed fatty acid, beef. This is the grass-fed beef. And you can see the amounts, okay, in these two. You can see that this is grain-fed, so beef from cattle which was fed with grain. Look at the others. We're getting approximately 20 milligram per gram. The bottom diagram here is beef from cattle fed with grass. And here the values are lower. Same fatty acids found. And then we calculated the ratio. Remember, everything is the ratio, right? Not the individual amount. Not the amount of the omega-6 or omega-3. It's the ratio of the omega-6 to the omega-3. This is the grain. Beef from... What our results is showing is that beef from grass is healthier than beef from grains. Okay, that's what it's showing. So we tried to do principal component analysis to see if we can separate the two. And look at the results. This is the grain beef, this is the grass beef samples, nicely separated using principal component analysis, even though the fatty acids present in the two types of beef are the same. And here shows the fatty acids also nicely separated using principal component analysis. So the take-home message now from this presentation is grass-fed beef is healthier. All right? So if you have to spend a little bit more money on grass-fed beef, do. It's good for our health. All right? And so we developed a method to be able to establish that, and using principal component analysis, we're able to discriminate between grain and grass-fed beefs based on the omega-3, omega-6 content or amounts. So I've come to the conclusion of my talk, and I would like to thank those who have helped me in my research at Thompson Rivers University. I would like to thank my university for their support. I would like to thank Canada Foundation for Innovation for giving me money to buy the capillary electrophoresis instrument. I would like to thank NSEC for supporting my research over the years. I would like to also thank Western Economic Diversification Canada for providing money to buy the ELSA. And then finally, I would like to thank America, the organizers of America.